So in this problem, we're being asked to use a geometric series to write the repeating decimal 0.0606060606 as a ratio of two integers. Now at first, it seems like it has nothing at all to do with the geometric series. But it does. So let me show you how. So remember that 0.06 repeating is equal to 0.06060606. I'm just going to stop there. That's enough. But you get the idea. All right. So now let's break that down just a little bit. So this one right here is 0.06 plus, and then the next set right here would be O, because the first two places are zeros. O is that zero right there, and then a 6 plus, and then I'll do this one in blue, 0, 0, 0, 0 for the first 4, and then another 0, and then a 6, and you get the idea. At least I hope you do. So I'm running out of paper space. All right, so now let's think about this as a series. This is really 6 over 100 plus, and then this one is 6 over 10,000 plus, and this is 6 over 1,000,000, because tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions. That's the millionths place. Plus, and I'm just going to dot, dot, dot. Continues on like that forever. Okay, but 10, or excuse me, 100 is 10 squared. 10,000 is 10 to the 4th. And 1,000,000 is 10 to the 6th. There's a pattern here that we can use in order to build this. Let's think about this. This would be the 0th term right here. So this would be n equals 0 right there, because we always start a geometric series at the 0th term. Then this would be 1, the first, or n equals 1 term, and this would be n equals 2. So the first term is 0, the second term is n equals 1, and the third term is n equals 2. And now why am I doing that? Well, let me go back real quickly. Remember that a geometric series, in order for this formula to work, look very carefully, we have to start at k equals 0 for this formula to work. So I need that first term to be the 0th term. If it's the 1th term, the first term, then we'll have to deal with it another way. In other words, if it's k equals 1. So it's a weird counting problem, because the first term is actually the 0th term. So we might want to make a note of that. So for these formulas to work, for this particular theorem to work, the first term must be k equals 0. Right? Just something to pay attention to. That's a frequent counting trick, and we will use it here because the theorem does not work, well, it does not work directly if we start anywhere else. So we have to have this be n equals 0, this be n equals 1, n equals 2. So this is the first term, but it's the 0th term. And then this is the 1th term, right? N equals 1 and then equals 2. So the language is a little strange, and that's a pretty common problem with counting, as a matter of fact. All right, now what in the world am I doing here? Well, I'm trying to make a formula. So, and I'm hopefully you're being able to see it. So it's 6 times, and then I have 0 turning into 2, 1 turning into 4, 2 turning into 6. So there's a pattern here, right? It's not only even 2, 4, 6, but it's also larger. So let me think. There's a few ways you could do this. So we could say that this is equal to, from n equals 0, or if you like k or n, those are the two common index letters. So to infinity, and it's 6 times 1 over 10 to the, and then we need to come up with a pattern for this. So it's something that involves n, something that'll go from 0 to 2, from 1 to 4, and from 2 to 6. I think 2 to 6 and 1 to 4 are the key here. So I need to take 2 times 2, that'll make me 4. 4 plus 2 is 6. 1 times 2 plus 2 would get me 4. So that will work. So if I go 2n plus 2, like that, that would work. Well, it's a little cumbersome. It's not quite fitting in nicely to our beautiful formula. So if we look at our geometric series, it doesn't have anything about, r to the k, 2k plus 2. It has r to the k. So I need to break this down a little bit more to make the ratio work in the way that I want it to. Well, that's all right. We can make that happen. So let me think of it another way. So this is really n equals 0 to infinity. Okay, well, I'm going to break this down into, so instead of making it this, I'm going to say 6 over 100 times 1 over 10 to the 2n. That's closer, right? Because 6 over 100, if I put 0 in here, that'll all turn into 1. So I'll get 6 over 100 for the first one. And then if I put 1 in here, n equals 1, then that'll get me 100, right? 1 over 100 times 6 over 100 gets me 6 over 10,000. So that's good, right? So basically what I did, see this plus 2? I broke it out, right? I said, okay, 10 to the 2 is 100, so I just made 6 over 100. So that's what I'm doing right there. And so now I'm super close, right? I've got 2n now, and if I look at the formula again, it has to start at 0, and it has to just be n, right? Or k and k, or n and n. So I can't have the 2n like I do. Okay, well, what would 10 to the 2 be? 10 to the 2 is 100, right? So I can rewrite this as n equals 0 to 100. So I still have my 6 over 100. I'm just going to write that right here. 6 over 100, that's from that bit, right? Actually, I decided to rewrite it in pink just to make it very clear. So it's 6 over 100, which is coming from that plus 2 part, right? And then I'm going to write it as, instead of 1 over 10 to the 2n, I'm going to take 1 over 100 to the n. And now double check that it works. So if you put in 0 for n, you'd get 6 over 100, right? Because this whole thing would be 1, right? Anything to the 0 power is 1, other than 0 to the 0, which is indeterminate. We'll deal with that some other time, right? But 6 over 100 times 1 would be 6 over 100. Now, if I put in 1, n equals 1, I would have 1 over 100 times 6 over 100, which is 6 over 10,000. Perfect. Now, if I put in 2, I would have 1 over 10,000 times 6 over 100, which would be 6 over a million. So it works. And what's beautiful about this is now we have our formula. There's A. A is 6 over 100. And then, and of course you could reduce it, but why bother? And then R is, I'm running out of colors. Let me grab light purple. R is 1 over 100. Nice. Nifty. So that means that I can now use the formula. Now, I could not use the formula until this point. So even though this pattern here is correct, it doesn't fit the theorem formula, the theorem pattern, right? So when you look at the pattern for the theorem, it says it has to be at 0, and then it has to have A times R to the K. It has to be in that form. And then this will be true, right? As long as the absolute value of R is less than 1, right? So that's the theorem that I'm trying to match. So even though this definition or this series matches that series up here, even though that's correct, it won't work for us. So that I played with it. I got the 2 out of there. That's closer, right? I'm getting closer to just n. And then I broke the 1 over 10 to the 2 out, and that gave me this. Right? And then this fits the pattern. I have my A right here. I have my R right here to my n power right there. And since R is less than 100 or less than 1, that means that it converges. Well, technically the absolute value of R is less than 1, right? Therefore it converges, and I can write what it converges to right now. So therefore the series converges to A, which is 6 over 100, times 1 minus R, which is 1 over 100. All right, well, that would be 6 over 100 times or divided by, excuse me, divided by 99 over 100, which lo and behold is 6 over 99. Yes, 3 goes into both of those. So if you want to reduce it, 3 goes into 6 twice, 3 goes into 99 33 times. But unnecessary. Right? It said to write it as a ratio of 2 integers, and I did so right here using the geometric series part. Right? It said to use a geometric series to do this, and that's what I did. So the hard work here is laying this out and figuring out the geometric series that will match the pattern that's in that formula.